Thanks very much for your time, Mahesh. This is Mike Anthony, Mahesh from Ohio State University. This is the May 19th teleconference of the Education and Healthcare Facility Committee. And Mahesh was giving us an overview of what he's doing at Ohio State. So Mahesh, what I will do is I'm going to give you control of the mouse, or if you like, I can simply cut over to your computer and you can show us what you want us to see from your computer. What would you like to do?
I'm fine with you giving me control of the mouse.
Okay, so I'm going to make you the keyboard and the mouse, and if you wiggle it around, you should be able to move. Okay, there you go.
Yeah, yes. All right. Hi, everybody. My name is Mahesh Ilindala. I am a faculty at Ohio State University. I work on the topic of microgrids. Since the past 4 years, I've been here. Prior to that, I worked in Caterpillar. So, one moment. Yeah, this page, it gives some brief introduction about me. These are my areas of interest: power electronics and controls for smart grids, microgrids, distributed energy resources, electrical energy conversion and storage, and also on the side, I do advanced electric drive transportation systems because my past experience at Caterpillar involved the electric drivetrain for the heavy machinery. But for the major part, I'm working on the microgrids. And if you see, I have been very active in the industrial and commercial power systems. So here are my recent publications. Sorry, let me move up. And most of them have been on the topic of microgrids for the past 2 years. And I'm very active in the Industrial Commercial Power Systems, the conference, as well as the Industry Application Society annual meeting. And I'm looking for new topics for application of the concepts of microgrids. I'm interested in these educational and healthcare facilities. So we had recently presented 4 papers at the Industrial and Commercial Power Systems Technical Conference held at Calgary. These are the 4. And I also wanted to talk a little bit about my other research work, which this is my research group page, Flexible Distribution of Energy and Storage Resources, FDERS. And this is a relatively new concept that we proposed in the around 2012, and it was mainly for industrial microgrids, which are in an islanded mode, because if there are smaller rated distributed energy resources that have to supply to harsh and demanding loads, which are typical in industrial power systems, then it makes sense to work together. The multiple DERs, that is distributed energy resources, can share the load burden in a way that is optimum, similar to the V-shaped formation in a migratory bird flock or a peloton formation in a cycling marathon racing team. We can have cooperative formations within the DER interconnection, and this can be controlled to take advantage and achieve savings such as enhanced controllability, increased resource lifetime. Here are they listed: optimal energy storage deployment, and improved system robustness. So these are the benefits, and we have published papers demonstrating these benefits.
I think this is the one that this is what you presented, one of the 2 sessions I sat in on. I think this of yours, this is the one
Yes.
I saw. This is the one that got a little bit of backing from American Electric Power. It was like a 250 kVA system.
Now, this has not been physically demonstrated yet. We have shown these benefits through models and simulations, mainly because the lifetime benefits are seen over a period of 5 to 7 years of testing, and there are models which are validated models available. But then doing physical testing needs a lot of resources and funding, and I haven't yet been successful. I'm applying for funding. I'm waiting for getting some funds to demonstrate it physically. But we have...
How much money do you need?
It needs a sustained funding support for about 5 years for 2 students.
So what does what is dollars? I guess what does that?
In terms of dollars, I would say that it needs some $600K or so.
Is that over the 5-year period?
It is, yeah, it is over a 5-year period.
Yeah. Okay. So we're roughly $100,000 a year. Okay. All right. So just trying to get a sense of the number, and what size is this? What is the load? I guess that was what is of interest to me. Is this is obviously scalable upward, right?
Yeah, it is scalable upward. Yes. And but here, this is shown to be like here in this particular case. If you see this figure, I mean here I have the link to the. I have the link to. I'm sorry, I don't know where it went. This is the basic fundamental theory or concept of this flexible distribution of energy and storage resources, or FDER, as has been published in this particular magazine paper, which will be coming out in September of this year in the IEEE magazine. And it explains the basic concept. Its benefits of extending the battery lifetime have been shown over a longer period, and that has been shown for industrial power systems. So typically crusher conveyor loads, and which have very sharp or a very sudden, abrupt load changes, large fluctuating loads, they are shown to be needing some energy storage support because of smaller distributed energy resources that don't have enough inertial response capability.
Mm-hmm.
And if there is no energy storage support in the microgrid, when it is operating in the islanded mode, these DERs can shut down when there are large swings in the load side.
I think after the talk I asked you, this was a stone crushing application, and this was the second one I sat in on. I wondered if there was a way for us, if this can be used in the district energy plants of hospitals or campuses. We have a number of them. I usually use 300. We have 300 relatively large district energy plants on the order of 100 megawatts. So say 10 to 100 megawatts in our industry. And I was just wondering, is this applicable to those types of installations that are already in operation? That's the question.
Okay. Now, my thoughts are along these lines. Typically, the loads in the hospitals or even residential or educational institutions are not as large and fluctuating as the stone crushing facility.
Oh yeah, it's a big, it's a manufacturing. It's a different type of load. I do get that. Yeah.
Right. So on the other hand, our what we envision in the future is a higher renewable energy penetration. So that, say for example, the load is by itself not a large fluctuating kind of a load, not a harsh load, but a very smooth load profile. Now, when it is superimposed on a large along with some renewables which are fluctuating due to the intermittency of the solar or wind generation. So I see these renewable energy as a negative load.
Mm-hmm.
So the net load, which is the difference between the real load of the system minus the renewable intermittency, can be seen as a fluctuating demand for any dispatchable sources, because I'm assuming that there are going to be some dispatchable sources to meet the reliability requirements.
Mm-hmm. Yeah. Well, when I also, in the back of my mind, when I saw the stone crushing application, and now that you've clarified, this was one of the questions I was going to ask at the conference, was we have actually a similar type of load that's like stone crushing. And it may surprise you that many of our larger football stadiums, for example, even some of the basketball stadiums, will have a very we have a peaky load maybe 10 times a year. We may go from double and triple a load. We may see a football stadium with a 1 megawatt load when there's nobody in it, but then we put 100,000 people in it, it's up to 5 megawatts, and it can move around quite a bit, especially when there's lights involved. So in the back of my mind, I'm thinking, what load is variable enough in a short period of time, spiky, so to say, as a stone crusher. And I thought about a football stadium, going from 2 to 500% load in a 10-hour period. So anyway, what is your thoughts on that? Just it's meant to be a bit of an anecdote, but I mean, there's some. It strikes me that if you're dealing with this technology with that type of variable load, that there's maybe some applicability.
Well, yeah, there is. It's just that the advantages or the benefits, the benefits, the time period is going to be different. So the particular case of stone crushing facility, we have found the benefits to be witnessed within 3 to 5 years because of the specific load profile that we had seen at that kind of a facility. But now with a football field, and just as you described, say a few peak load scenarios each day, you might see them the same kind of benefits happening instead of 5 years. You may see that over a longer time horizon. But then the case is this thing. Everyone is talking about some new technologies. They demonstrate those in terms of performance and improvement, and do the testing for 5 minutes or maybe 15 minutes. it can be shown in the form of some waveforms and say that this is superior, but we have not yet deployed these microgrids out in the field, or they are just now coming out, and we don't have data on a longer time horizon how they will perform over a longer time horizon. Some of these technologies are not suitable, or I should say that they don't survive long enough. And this particular concept of FDERS, I think, it will make a case or more convincing argument about it will be known once we see all these different microgrid technologies getting deployed out into the field, and we see that some of them don't survive for long periods.
Yeah, that's fair. That's fair.
But our experience, having worked on microgrids for a long time, has given us this insight to look far beyond the current limitations, and it's going to be difficult for somebody who is just now beginning to understand this concept, because and even to convince them of this, we try to explain based on this formations, like birds. I don't know whether this is clear here in this particular slide.
I can make it a little bit larger. Can you click it? I believe maybe I have to click it. There we go. And then I'll make the screen a little bit larger. And I think you might be able to.
Yes.
Does that help? I think you can move it. Oops. I think you can move it around now. What did I just do? Oops. I'll find it for you. Just be patient. There you go. And okay, go ahead. You can move it around.
Yeah. Okay. If you see, the way we explain is that there are published papers on ecological sciences in the journals Nature and Science. They published about these birds in a V formation, migratory birds. It seems they travel longer distances when they are in a formation as against going alone. So what happens is the leading bird is able to block the air and allow the drafting bird to put in lesser effort in joining in the formation. Now, of course, the leading bird gets tired faster than the drafting birds because the leading bird is taking the hit all the time. So what they do is, when they travel over longer distances, they exchange their positions within the formation, and that way they extend their endurance limits. And this kind of a similar cooperative formation we can observe in cyclists. In racing teams, they have a peloton formation, and what they do in a peloton formation is that they'll be rotating their positions when they run or when they race over kind of cycling marathon races. And so the last one in the formation is actually drafting and not getting the same kind of resistance, not facing that kind of resistance as the front one. So they rotate their positions in such a way that every one of them can relax a little bit when they are tired, staying at the front, and can recover. And so they extend their endurance limits to race over longer distances. Now, in a DER formation, microgrid consists of multiple DERs, which are interconnected. I'm trying to go to the next page.
Would you like me to make the page a little bit smaller so you can see more of it?
I think this is fine. You see, a traditional distribution system, the main grid connection is here, and these are the different distribution feeders. In the case of a microgrid, the DERs are connected in the feeders near the load, and you see that this can be also viewed as a formation, like we have seen the cyclists or birds. Now, in the case of birds or cyclists, they cooperate with each other, and they have to rotate their positions in order to extend their endurance limits. Whereas in the case of DERs, what we do is we assume that they are going to do their job well over a longer period, and we do not look at that, or we did not start to look at those longer time horizon issues yet. And that is what I tried to say, that these DERs, if they stay in their positions because of this physical interconnection through the feeders, which are fixed connections, effectively they are like fixed in their formation wherever they are located. And say there is a large load demand, fluctuating load demand. This is an industrial load demand, and this is, say, a crusher facility. Then the way I look at it, analogous to the bird V formation or the cyclist peloton formation, is that the DER which is located closer to this is like in the leading position, and the DERs which are farther in the line because of these network impedances, effectively they are farther in the formation, and they'll stay as they are because the physical impedances are going to be constant. They cannot be changed, and we cannot physically move them. Once they are connected, once we have these installed at these locations, effectively the formation is fixed. And that, I say, is not the best way to have the microgrid for a longer period. And so I propose that it is better to keep it flexible. Now, how do we make it flexible? That is by having the flexibility through the controllers. We can virtually relocate the DERs. Even though physically this DER is located here, it can be made to virtually work, function as though it is located here.
That's an expensive source, but I know the utilities do use that in their, if there's a regional contingency, they are moving those on flatbeds. They'll run a couple megawatts for voltage support in certain areas. But there are, I guess I'm looking at this, I see some price, there's some price and cost discovery has to happen here.
Yes, I hear it's just an example. I showed the wind, the combined heat and power, CHP, the reciprocating engine genset, fuel cell, solar. There is energy storage support for the intermittency, or when the response time is not adequately fast, then there is some energy support. But these are just for examples' sake. And each one has its own behavior based on its fuel source or its controller. And so it's effectively, if we look at it as a formation, like cyclists or birds, it is like unequal team members. They're not similar. It's like, there is a weaker team member. If you see the behavior of all these DERs, they're not the same.
Right. Plus there's interdependency between this fuel cell natural gas and the CHP natural gas. That interdependency complicates the equation.
Oh yes. Yes. You're right. Now, there can be also that economic or the cost function, some kind of an optimization that can be also included or in the objective. See, my initial objective, as I said, was to get the benefits of extended lifetime, and I could see this analogy with the bird V formation for extending the lifetime of the energy storage in the microgrid. So because extending the lifetime is similar to extending the endurance of the team members of these formations. But we can also see that not all members are equal or identical. In the case of bird V formation, typically we envision that all the birds have the same ability. They are equal. In cycling racing teams, usually all the team members are experts or are professionals. But say there are amateurs and there are professionals, and there are weaker ones in the team and there are stronger ones. We would want to have them arranged in such a way that the stronger one is leading most of the time and the weaker ones are able to draft behind. Otherwise that group will not survive. And similarly, even in the DER formation, we have seen that they are all not identical. And now cost, you brought up a good point that even economics can play a role. The one which is more economical can be made to take the leading position, and the one which is expensive can be made to take a drafting position. So even it can be dropped off if necessary.
Well, it strikes me that this paper deserves a lot more vetting. I don't know. Do you have the PowerPoint for this one, or the PowerPoint that you presented for ICPS? Do you still have that one?
I guess my student was the one who actually presented, so the copy of that presentation I did not. I don't have the latest copy.
Well, I'm going to invite you sometime in the next weeks or months or whatever it's your convene, if they would like to represent it. As I say, we put it on our channel. You can even use it off of our. If I can say that we are dealing with some of the issues that are presented to campus power engineers, and I think this is one of them. We're all subject to the. There's often political pressure to try to respond to some of these ideas. So this is clearly something that we probably should do more. As you probably can see here, I have a call coming up at 10 o'clock. And so,
okay.
But what I did want to do is I did have some questions.
Yes.
And what I'm going to do is tell you where our numbers are and give you a little sense of, I'm going to give you a little bit of a sense of where I see. I'm going to give some numbers here since this will be my blackboard, okay? And I think you can see, and I'm going to give you some order of magnitude numbers. So right now, the U.S. education industry, this is what we spend. So I get my numbers right here. This is how much we spend per year on salaries and everything. Okay, that's large. That's the industry is a 1.2 trillion. Of that, we spend about 300 billion on facilities, and that's labor, energy, new construction, O&M, security, etc., etc. And that's both for healthcare and for just educate. That's K-12 and university-affiliated hospitals. So I'll say it includes K-12 and university-affiliated hospitals. Okay. Of that, we spend about 30 billion on energy. Is our industry's energy bill. So the question I have is, knowing that there's a lot of, and let's just say half of it is, half of it is natural gas and half of it is electricity. My job is to try to get 1 to 2% out of this, and so I'll go to our website and I'll show you that to give you some order of magnitude numbers. And again, here's our About Us site, and this tells you that this is roughly our spend. This is what we've been able to do with standards advocacy, and this is probably Ohio State has actually benefited from this. Now, should they decide to use these, there's many opportunities we've created for them. Okay. But they may not have taken advantage of. So in general, that's what we're trying to do here. And here's the numbers. As you can see that we spend a lot. Harvard's endowment's only 30. That's roughly Harvard's endowment. Okay. So my job is to try to figure out how to get this bill, if I can take a couple percent out of that. So if I can take minus 2% out of that, if I'm not mistaken, that's something to take minus 2% of that would be roughly, what is that? That would be 300. That'd be 600 million. So that's what's in play right now. So my question is, overall, by installing smart grid technology, will it help me reach my goal of trying to get about 600 million out of, and let's say there's about 1,500 colleges and universities, and I think there's about 200,000 school buildings. I think I've got that right. K-12 school building. So those are the numbers I have to steer by, and I'm trying to get this here. And my question is, and that you don't have to have an answer right now. This is what we're trying to do. We're looking for everything possible. We do know that microgrid concepts are very high on the agenda of our industry's leaders. So we're responding to them. But ultimately, those same leaders are going to say, how much did I save, or how much avoided cost did I make? Could you respond to that? It's kind of an unfair question to have you answer in 6 minutes, but I just wanted to know how you respond to what we're trying to do here.
So let me get it right, whether I understood it correctly or not. You mean to say that we have to show that 600 million can be saved, is it correct?
We would like, our benchmark is about 2% per year. It's either real actual savings off of our bill by energy use reduction using the methods. And I should tell you, and this is another conversation, one of our projects, and we talked about it in Calgary, is that we believe that there's so much waste that our priority is largely trying to explain to the industry that building power systems are twice as oversized. So if I go here, this is just something I happen to know. Most building power system transformers are about twice oversized, sometimes 3 to 4 oversized. As I try to say, I don't mind when a transformer is 2 or 3 times oversized. I mind when it's 8 to 12 times oversized. And so our thinking is that the microgrids are being built upon systems that already have a large number of inefficiencies on it. So I've received some partial fund. I have 70% of this amount of money. And that's what we were talking about in our, at least in my session, back in Calgary, back in Calgary. And so that's why I have an interest in working with, I'm sorry, that might be one of your competitors. I want to work with Ohio State and all these other organizations that are doing microgrid. And microgrid would be one of the things that I'd like to see how Ohio State handles it. I guess we're all in the Midwest at the moment. So there's a lot of attention to microgrids, but how can I make them work for us within 6 within 6 years? How can I get to the point where, and that's where we can continue this discussion. That's where we can continue this discussion.
Yes. Now, see, I don't have the numbers yet, but if you see the fundamental approach that I have taken in my research, I'd say that we are looking at cooperative formations of the DERs, and the major cause of or motivation of going for that kind of a cooperative formation is because we want to optimize. We do not want to oversize any equipment. Like in the formation, all those individual players individually, or they cannot take the burden alone. They need to cooperate with each other, and they are not rated to meet that large demand by individually, and there's no way they can survive longer period without teaming up with each other and without rotating their positions or without being flexible. And although I talked about only one particular example of extending the battery lifetime, we have also found that we can improve the robustness of the overall system. By robustness, I mean to say the stability robustness, meaning in the event of unexpected events, any sabotage or extreme weather events also, this kind of a system is going to be more robust and resilient.
Okay, good. Well, I'm thinking we should set up another call. This ran over, and I do need to get on this other one. I've got 2 minutes to do it, Mahesh. Can I give you a call maybe early next week, and then I need time to read your papers, and let's see. As I say, I'm going to explain why campus power systems are the subject of a lot of political attention at the moment. We're an area that's not been. That's why we formed the electrotechnology. I'm going to grab the controls here. That's why we formed this committee, because we're anticipating that there's going to be, in fact we know it, that there's going to be quite a bit of attention to campus power systems, and we need to be able to answer questions. And so I think at the moment I have to close this call. What I'll do is I'll download this and I'll send it to you. I'm very grateful for your time. I'll post it on our meeting agenda here at some point. But as you can see, we try to be fairly active. I think a lot of us are still recovering from the Calgary trip. So that's my excuse for
it. Yeah, me too.
Yeah, me too. Okay. So look, thank you very much for your time, and I'll send you an email and set up another call, and let's look for some money to look into this stuff. Okay?
Yes, sounds good.
Great. Thanks very much.
Thank you.
Yeah, bye-bye.
Bye-bye.